So we will go over the optimization. When the necessary, let's say f of x is bounded below, then f of the necessary conditions for stationary points are f of x is 0. So the set of points that satisfy this are called critical points, and when critical points can arise at maximum dash of x is 0, they can arise at minimum dash still of dash of x is 0, and they can arise at certain points. So this is an example of minus x squared. This is an example of x squared. This is an example of x cubed. So each of this dash of x is 0, but here we attain maximum. Here we attain minimum. Here it's not maximum or minimum because in one direction the function increases and in other direction function decreases. All right, so just by knowing the first order information, we cannot conclude anything about the maximum, minimum for saddle points. So we need something on the information of second derivative at the point x. So here, if it is negative, in this case, it is -2. Then you have a maximum. And if it is positive, here it is 2, then you have a minimum. And here, it is 6x. So when x is positive, it is positive, and x is negative, it is negative. So it changes along the direction of x. Positive and negative. So we don't have any maximum. It's called as saddle point. So for multivariable, this still holds, but here instead of just looking at the second derivative, we need Hessian matrices. So for example, in two variables, f of x comma y, Hessian is composed of partial derivatives f x, assuming they exist and they're continuous. So this holds. I mean, fxy is fyx when they are continuously differentiable. Okay, so here we check the determinant, and if the eigenvalues, we check the eigenvalues. If one is positive and one is negative, we have a saddle. So let's solve some questions. Also, if f is convex, so the function is convex if it satisfies the following: f of alpha of x, versus convexity whenever so for example, a function of this sort is convex, and take this x and this y with some alpha. So this alpha, this lies here, and the function always lies below the line connecting this f of x and f of y. And this value somewhere lies here. So the function value is lower than the interpolated value. This is convex. So whenever the function is convex, we have a minimizer, and the local minimizer is same as global minimizer. So here we cannot guarantee that we always find global minimizers for the general functions. Only for convex functions we have that property you can minimize. So let's solve some questions. The question is square plus y square minus 2x minus 6y plus 14. Of x comma y square plus y square minus 2x minus 6y plus 14. So square minus 2x plus 1 plus y square minus 6y plus 9 plus 4. We can rewrite the above equation as like this. This is nothing but x minus 1 whole square plus y minus 3 whole square plus 2 square. So here we can see the function x minus 1 whole square is convex, and y minus 3 whole square is convex in y. And when we add non-negatively, it is again a convex function in both x and y. So as we know that when the function is convex in both x and y, we have the local minimum is same as global minimum. And it is pretty easy to see what is the minimum value that it can happen, because these are positive squares. The lowest value it can take is 0. That happens at x equal to 1 and y equal. And the minimum value of the function is 4. So f has exactly 1 point of local minimum, and that 1 point is global minimum, and that 1 point is nothing but 1, 3, and the minimum value itself is 4. Second question, the function is x power 4 plus 4 minus 4xy plus 1. And the origin has saddle point or not is the question. So we will solve that. For x comma y, that is x power 4 plus y power 4 minus 4xy plus 1. So we compute the first partial derivative of f with respect to x. We get 4x cubed and minus 4y. And fxy is where we get 12x squared minus 4. Because of symmetry, fxx nothing but 12x squared. Because of symmetry, fyy is symmetry of the function in x and y. We have 12y squared and fxy again, right? It is symmetric. And this thing fyx and fxy will be so fxy will be minus 4. We need to differentiate this with respect to y and we get minus 4. So the Hessian is 12x squared minus 4 minus 4 12y squared. At origin, the Hessian becomes 4 minus 4 minus 4. And the eigenvalues are lambda squared and minus 16 equal to 0. So we see one on one direction, on one eigenvector, the function value increases. On another eigenvector, the function value decreases. So it has saddle point at origin. So we have a rectangular box which has an area of 12 square. What is the maximum volume of the box? And notice that this is a box without lid. So let's try to do that. And there is a sheet of area divided m square. This is supposed to be converted to cube. So call this side as x, call this side as y, and call this as z. Assume that one of this side is open, and we get an area of x times y plus 2 into yz, and assume that one is open, zx. So this side is open. This is equal to 2m squared. But then we want to maximize the volume of this thing, which is nothing but x, y, and z. So this can be solved using Lagrangian, and it is a bit lengthy. And once we solve the Lagrangian, that is x, y, z minus lambda times 2xy plus 2yz plus zx minus 2lm squared of x, y, z, comma lambda is this. Do y plus z is 0, and x z minus lambda. Y 2z equal to 0, and xy minus lambda times z x plus 2y equal to 0. So we need to solve these equations and find out the maximum value of x, y, and z. With satisfying this constraint, of course. So that will yield a solution of 4m cubed. So yeah, so second question is, and the question is, need to integrate this function x minus y square over the area dx going from 0 to 2, y going from 1 to 2. So this is nothing but x squared by 2 minus 3y cubed, 3y squared x. So it's going from 0 to 2. At 0 it is 0. So at 2 we have 2 minus x y square. Y is going from 1 to 2 dy. Y means 2 y cube. So it's going from 1 to 2. 4 minus 16 minus 0. So it's minus 2. So that's the answer. And you need to integrate this function over this area and see what happens. So function is sin of x comma y is 1 to 2 0 to pi. Integration of this respect to going from 0 to pi. X going from 1 to 2. Times dy. So x times y. So here we get minus cos of x comma y divided by y. X is going from 1 to 2. And this is cos of 2 cos of x minus cos of y minus cos of dy divided by y. And there's y here that get cancelled. So this is what we have. And each of this things has z here. So the overall of those things. So let's solve another question. Stationary points of this function. Function is x y equal minus x squared minus y squared. So fx, we set this aside and we just set this to 0. And differentiation of this needs to be with respect to x needs to be set to 0. So that is equal minus x squared times then equal minus x squared minus 2x squared is 0. and this is 0. So one solution is y0, and the solution is 2x squared equal to 1. The symmetric in x and y we have that 0, 2 squared 1. So yeah, so that's why we have this as the stationary nodes. Y square, and it lies in the positive arc. So f of x comma y is x times y squared, and the constraint set is and x squared plus y squared less than or equal to 3. So the constraint set is the arc of radius root 3. Root 3. So and we want to know the maximum and minimum values of this function. The minimum value is pretty easy, x, that x is equal to 0 and y is equal to 0. The function takes a value of 0. What is the maximum value? So y squared is less than or equal to 3 minus x squared. You can substitute this here. X into 3 minus x squared. And let's try to find the critical points of this. So this we get 3 minus x squared equal to 0. So x equal to 1. And substituting that, you get y is equal to 2, square root of 2, and x into y squared is equal to 2 as the maximum value. So 2 and 0 is the answers. Let's see this. The question is squared plus y squared plus z squared subject to constraint. Squared plus y squared plus z squared y plus yz plus zx is x plus y plus z. this, if you treat x as the vector x bar, so this thing is nothing but minimizing x squared with the constraint 1 transpose x equal to 1. So taking Lagrange and we get so again 2 times 1 transpose x that's equal to lambda times 3. This is 24, that gives lambda as 8. And then x bar is equal to 4 times 1 bar and 16 times 1 transpose 1. This is 3. This is 48. And the last question is the region is 0 to 1. Cross by line. Is this statement true or not? So sine pi x at x equal to 1 by 4, it's a value of 1 over square root of x. And as a function of x, as a function of y, cos takes a value of so 1 by 4 to 1 by 2. And takes a value of 1 over root to 0. And it's a product of two positive functions. It's always positive. The minimum value it can get is 0. So that is given by the right side. And the maximum value we can get around this is take the max that it attains. The maximum value of this is over root 2. Max of this is again 1 over root 2 times the entire area, which is nothing but 1 over 4 times this is again 1 over 4. So this is 1 over 2. So it's true.